Modern petrochemical facilities are vast, continuous systems. Thousands of gallons of volatile fluids move through these towers and piping every minute. To increase capacity, operators frequently need to integrate new infrastructure, like a massive crude oil storage tank or a heavy-duty pump, directly into the existing layout. The engineering challenge lies in permanently connecting this new, isolated piping to the live process system. This connection point is known as a tie-in. A tie-in represents the exact moment where the theoretical math of plant design meets the highly volatile physical reality of active chemical production. Inside an active pipeline, crude oil, natural gas, and toxic byproducts like hydrogen sulfide surge through the metal under intense pressure. Breaching that steel barrier without absolute control introduces an immediate ignition source to flammable hydrocarbons, or releases a lethal cloud of invisible gas. The 12-step tie-in procedure is a sequential risk mitigation framework designed to systematically neutralize these specific hazards. Understanding a tie-in requires mapping each of these steps directly to the physical risks they are engineered to eliminate. Execution begins by verifying the exact line number on the engineering schematics. Misidentifying the target line is often a fatal, irreversible mistake. Accurate identification ensures the team is targeting a line that is prepared to be taken out of service. Steps 2 and 3 involve the risk assessment and permits, where the job safety analysis translates engineering theory into operational safety rules. This requires a strict hierarchy of permits to work, specifically differentiating between cold work and higher-risk hot work permits. These documents provide theoretical isolation, identifying and neutralizing hazards before a tool ever touches the pipe. Step 4 is physical isolation. Upstream and downstream valves slide shut, blocking product flow. Padlocks and warning tags lock onto the closed handles, providing a mechanical guarantee against accidental operation. The line is then depressurized. A drain valve opens to remove trapped product. Finally, venting clears out residual explosive gases until a gas-free certificate is issued. Full mechanical isolation is the absolute prerequisite that makes a volatile system a survivable workspace. Step 5 requires continuous gas testing. Even on an isolated line, monitors must confirm that the explosive gas levels remain at 0%. Steps 6 and 7 cover the initial breach and fit-up. This involves cutting the line and the precision preparation of the pipe bevel. Alignment, clamping, and root gap spacing are critical here. The two sections must be perfectly positioned before the permanent joining can begin. Step 8 is welding. This is the phase of maximum vulnerability because it introduces a direct ignition source into the plant environment. To maintain safety, only certified welders using an approved welding procedure specification are permitted, supported by a dedicated firewatch. The safety of this weld depends entirely on the rigorous execution of the previous 7 steps. In Step 9, standard visual inspection is insufficient. Structural integrity must be verified through non-destructive testing. Techniques like radiography or ultrasonic testing use high-frequency waves to inspect the internal, microscopic structure of the metal for flaws. Step 10 is the hydro test. Hydrostatic pressure simulates operational loads to guarantee the new connection is leak-free. The final steps complete the integration. After anti-corrosion painting, the locks are removed, the line is flushed, and pressure is normalized during commissioning. These final verification steps officially incorporate the new pipe as a permanent, load-bearing artery of the existing plant. This 12-step sequence represents a cold tie-in, which requires a full system shutdown and depressurization. When shutting down a critical pipeline is impossible, engineers utilize the hot tap as a necessary alternative. The mechanical reality of a hot tap involves drilling into a pressurized pipe without halting the flow of the product inside. This method carries a significantly higher risk profile and requires specialized equipment compared to a standard tie-in. The choice between cold and hot methodologies is a calculated trade-off between the economic cost of a shutdown and the operational risk of live-line work. A process plant exists as a balance of extreme physical forces. In this environment, safety functions as a precise sequence of applied mechanical controls. The tie-in procedure is the engineering framework that allows massive industrial infrastructure to grow, adapt, and expand without catastrophic failure.